For our project plan, our group decided to research on the different types of microfluidic device designs which would be suitable for our experiment. We used the LibreCAD software to design all of our microfluidic devices. During my research, I read that the shape of microfluidic channels is very important in deciding the behavior of the flow, and such channels are designed to ensure efficient mixing of reagents, samples, and to minimize dead volumes. Staggered herringbone mixers and serpentine channels are two of the passive designs that are usually incorporated in microfluidic devices to enhance mixing via chaotic advection. I then decided to implement a simple design of the serpentine channels into our LibreCAD design, and will keep testing and improving on this simple design until it was able to effectively produce the results that we need. As for the execution, we came up with many different combinations of acids, concentration of bases, and pH papers to be used. For our very first experiment, we decided to use high acid onto pH paper 1 alone on one side, and high acid flowing through a low base concentration into pH paper 2 on the other side, as we thought that we were only supposed to show the pH paper changes color based on the pH. Once we realized our mistakes, we also realized that our design was not complex enough to carry out multiple experiments. So we went back to research again to improve our design and to come back again for multiple sessions to test and improve our design until we could carry out a few experiments whilst having a good complex design.
In the development of a microfluidic device, we went through several design iterations to optimize functionality and performance. Starting with the first version, we identified a lack of complexity and the absence of compartments for reactants. To address this, the second version included dedicated compartments to hold reactants separately, enhancing control over mixing and reaction processes. We also split the track to allow for more tracks for separate testing, enabling multiple tests to be conducted simultaneously and improving the device's functionality. Additionally, we transitioned from purely curved paths to straight tracks with curved edges. This design change was made to improve control over fluid dynamics, providing more predictable flow and gently redirecting it to maintain stability and consistency. Moving on to the third version, we removed the middle circle at the start of the device, replacing it with a more streamlined design. This adjustment was aimed at reducing initial flow resistance and optimizing the entry of fluids into the device. We balanced the split at the start and at various divergences, ensuring that the flow paths were more consistent and reliable. We also focused on making the pathway widths more symmetrical. This symmetry helped in maintaining even flow distribution, crucial for precise particle handling and reducing potential dead zones. Finally, we elongated and fitted the air holes. This change was intended to improve airflow regulation and prevent blockages, thereby enhancing overall device efficiency.
For our final product, we have made several key improvements to our design. Firstly, we have added more lanes and compartments, which allow us to use more pH papers for testing. This significantly increased our testing capacity. We also incorporated well-defined flow paths that guide the movement of the solutions through the system, ensuring a smoother and more accurate flow. Next, we strategically placed circular compartments throughout the design. These compartments serve as the reaction chambers, optimizing the mixing and reaction of our solutions with the reactants. Additionally, we enlarged the air holes, which help regulate the flow and allow the air bubbles to escape more effectively. So, with these changes, we were able to obtain better and more accurate results compared to our initial design.
For our first experiment, we used high acid entirely and had a low carbonate on the left and a high carbonate on the right. With this, we wanted to see the pH of the solution when a high acid mixes with a high and low carbonate. On the left, we have pH paper 1 and pH paper 2. As for the left side's results, the color changes was present in both pH papers 1 and 2. This indicates that the high acid plus low carbonate solution was around pH 4 to 5, as both papers had changed color. We know that the low concentration carbonate was not strong enough to neutralize the high concentration acid. Now for the right side, we have pH paper 3 and pH paper 4. The color change was mainly observed in pH paper 3 and not so much in pH paper 4. From this, we can conclude that the high acid plus high carbonate solution was around pH 7 to 10, since pH paper 4 did not change color. With this, we know that the high concentration carbonate was strong enough to neutralize the high concentration acid.
In our second experiment, we mixed the ionized water with low and high carbonate. We used pH papers 3 and 4 to test the pH. The low carbonate did not change the paper's colors, likely because the pipette used had residual acid contamination from past experiments, preventing the pH from rising above 7. In contrast, the high carbonate changed the color of pH paper 3 but not 4, indicating a pH level between 7 and 10.
In our last experiment, we decided to use a low concentration acid throughout the entire process. We also used a high concentration carbonate on the right side and a low concentration base on the left side. We observed a color change on both sides. For the pH testing on the left side, we used pH papers 2 and 3, which measures pH ranges from 4 to 7 and 7 to 10 respectively. Both of these papers change color, indicating that the pH of the solution on the left side was around 6 to 7. This suggests that the low concentration base was strong enough to neutralize the low concentration acid. On the right side, we used pH paper 3 and 4, which measures pH ranges 7 to 10 and 11 to 14 respectively. Both papers had changed color. This probably means that the high concentration base neutralized the low concentration acid to a pH level between 9 and 14 as indicated by the color changes in both paper 3 and 4.